Now, when we want to discuss acid strength, we're going to split our acids into two main categories. Binary acids, which is a hydrogen attached to a non-metal atom, which we're representing here as HY. And we'll also talk about oxo acids, when a hydrogen is attached to an oxygen and a much larger structure, something else after that oxygen. Let's start with our binary acids. Now, to determine acid strength, we really need to talk about the structure of the binary acid and what is composing that hydrogen to non-metal bond. Now, the size of the non-metal attached to the hydrogen is very important for us to discuss. So when we're thinking about some binary acids like HF, HCl, HBr, and HI, notice I've just gone down the group 7A or 17 halogen family, fluorine, chlorine, bromine, and iodine. As we go down this list, those atoms being represented in our generic Y atom, right, the non-metal bonded to hydrogen. As we go down this list, size of Y, I'll put those in quotation, size of the halogen increases. And so what does that mean? It means that the actual length of the hydrogen to non-metal bond is increasing as well. And as that bond length increases, because of the size of the atom, the bond actually weakens, all right? So when we're looking at that strength of the bond length versus strength, we know as the bond length increases, the weaker the HY bond actually is. And so therefore what we see is that that bond is able to break easier. It's more polarized. So when we think about that ability of the halogens to take on some of these electrons, we remember this polarizing arrow where the halogen is delta minus and the hydrogen is delta plus. When we think about that size of the halogen, the larger the size, the better it is to hold on to a negative charge. We can kind of see that when we draw the conjugate bases. When we think of HY going to its conjugate base of Y minus 1, right? Some sort of base can come in here, take off that proton. Remember, to draw the conjugate base, you got to take those electrons from the HY bond and pop them onto Y. This is now our conjugate base. And that conjugate base, not only does the size of that conjugate base or the size of the atom Y affect the bond length, it also affects the ability of the conjugate base to be stabilized. So we have a lot of statements out, all right? Let's think about what all of these mean. As Y increases, all right, as the size of the atom Y increases, the bond length increases, that means it's a weaker bond. That means it's a better or stronger acid. All right, there's that home plate. What do we mean at the end of the day? It means that HI is the best acid, most reactive, fastest to give away its proton. HF is the weakest acid, the worst acid, not good at being an acid, all right? That's one factor, size of Y, all right? Bigger the Y, the better the acid. Now, when we think about the electronegativity of Y, this is looking at atoms that might be very similar in size. When we think about the hydrogen to carbon bond, the hydrogen to nitrogen bond, the hydrogen to oxygen bond or the hydrogen to fluorine bond. I'm going to go ahead and put the rest of those atoms to complete the octet condensed on the other side, just so that we can focus at one bond at a time, but know that the rest of the molecule is still there. Now, when we look at those highlighted acidic bonds, these atoms that are connected to the proton, carbon, nitrogen, oxygen, and fluorine, are all very similar in size. Yeah, we do know that size decreases a little bit as we move from left to right across the periodic table, but what really is changing is the electronegativity. The electronegativity of Y is increasing here. So as the electronegativity of Y increases, Y is becoming more delta negative, right? We get a more polar bond as we move. And yes, I'm drawing the arrows even bigger as we move from left to right here. And so what does that mean? That means Y is pulling more and more and more electron density away from the proton. The hydrogen, which is a delta plus, is feeling more like a proton. More like H plus, right? The greater the electronegativity of Y, the better the acid. So HF out of this group is the best acid. HCH3 or H to a carbon is the worst acid. Strongest acid is HF in this group. Weakest acid is hydrogen to carbon. All right, so two different factors of our binary acids. We want to think about size first of Y, the nonmetal atom attached to the hydrogen. Then we'll look at the electronegativity of that atom. All right. Oxo acids. Now, oxo acids have an acidic hydrogen attached to an oxygen atom. So we're comparing specifically atoms with this setup, an OH bond, and then oxygen is also attached to something else. Some really common ones, HNO3. When we think about HNO3, nitrogen is in the middle. We have oxygens all around it. Yes, we have some formal charges here, but overall we are net neutral. Practice with this Lewis structure before moving on. I think it's a really important one to be able to decide where the atoms go. Nitrogen goes in the center because it makes the most number of bonds. And when we're organizing these, we do have one oxygen to hydrogen bond. Now that is an acidic bond and it is an oxo acid. Now, the ability to have resonance in the conjugate base is what gives our oxo acids their immense amount of acidity. So we could think of a base coming in, pulling off that proton. Let's just draw the conjugate base of HNO3. It's the nitrate ion. Remember this molecule from last semester from Gen Chem 1? When we think about this atom, we talked about resonance, the ability of some electrons to move around a structure. I could have drawn that lone pair up at the top versus down at the bottom right. I could do the same thing where I popped this one to be the double bond. All of these are linked. These aren't reactions that I'm drawing these arrows for. These are just the interconversion of the molecule in its normal state. The pi bond, that double bond, can rearrange to any of these oxygens, all right? That negative charge, notice where it's popping around. Negatives, there's always two of them. don't forget my formal charge of +1, but notice the negatives are always popping around. They could be in different locations. That tells me that the molecule is stabilized. Not one atom is just holding on to that negative charge. It's sharing it amongst everyone. How sweet. The more oxygens you have, the more resonance you have in that conjugate base. And so the more resonance in the conjugate base, the more stable the conjugate base. And what does that mean for the acid? It means that the acid is reactive. We're going to start seeing this comparison. The reactive acids make stable conjugate bases. The more reactive the acid, the more stable the conjugate base. And it's because of this ability to move those negative formal charges around and share them around the molecule that is the stabilizing effect. The more oxygens you have, the more resonance you will have in the conjugate base. And so those more oxygens, 3 versus 2 versus nothing else attached in that very, very last one. We see more oxygens, more resonance in conjugate base, stronger the acid. Awesome. Now, strong versus weak. Strong acids are strong electrolytes, all right? They completely ionize, we'll say completely ionize in a solution. Weak acids, we've kind of talked about them before. Weak acids are what we call weak electrolytes. They can give up their proton, but they are not really good at it. Only a small percentage will do it. So this is where an equilibrium is established. Very, very important for us to realize that equilibrium is established between the acid, base, conjugate acid, and conjugate base. So there's a forward and a reverse reaction going there. Same idea, strong bases are strong electrolytes. They completely or near completely ionize in water, and they produce hydroxide through dissociation. All right, so we will see that Arrhenius definition still holding through. We'll talk a little bit about other strong other bases, but they will not be strong bases if they don't produce hydroxide. Weak bases can be our molecular bases or our covalent bases like NH3. The weak base is also a weak electrolyte. Again, equilibrium is established. The definition of producing hydroxide through dissociation or reaction with water is still apparent. We'll see the hydroxide, but again, we'll look at more definitions than just the Arrhenius definition. Stronger the acid is at donating the proton, the weaker the conjugate base. We just talked about that. When we think about that conjugate base being formed, the stronger we say the acid is, the worse the conjugate base is at being a base, right? The more stable it is or unreactive. The higher the oxygen number or oxidation number usually means the stronger the acid. So H2SO4 is stronger than H2SO3. HNO3 is stronger than HNO2, right? And we dealt with that because of resonance. The cation stronger acid is better than the neutral acid, okay? So if we see H3O plus versus H2O versus OH minus, all right? So when we're looking at those, it's dealing with the binary acids, but also formal charge as well. If you have a positive charge on an atom for a binary acid, that is going to be the most acidic form. The neutral form will come after that. And then the negative form is the worst acid,